The network is there, but not great.
Okay, let us see.
We are yet to get the fiber connection due to COVID.
So, good morning, everyone. Today we are going to welcome Professor Gopal Krishna Panda to give the webinar. And I welcome you, Dr. Panda, for this SOAWAL webinar. And actually, every Saturday we are organizing one webinar from and that is happening in all the departments of our university. And that's a very good step taken by our president, the founder, management president, Professor Manoj Ranjan Naik. And today, let me introduce everyone. Today's speaker, Professor Gopal Krishna Panda, who has been associated with the department since 1989 and is the senior most faculty of the department in NIT Rourkela. He has done MSc Statistics and MSc Mathematics, both MPhil and PhD from Sambalpur University. One minute, excuse me. He is also a very gold medalist of the year 1985 from Sambalpur University for securing highest percentage of marks in the total aggregate among all the students passing BA, BSc, become MA, MSc, NCOM in that year. That's so nice about you, Dr. Panda. Really, I also knew this thing at that time. You were the topper. And for the information of everyone, let me tell you, Dr. Panda was junior to me at Sambalpur University while I was doing my MPhil course over there, and he was doing his PG in statistics. Then he completed PG in mathematics, then MPhil, and then PhD. And now he's a very senior faculty member of NIT Rourkela. His research interest lies in the field of number theory and nonlinear optimization. He has more than 90 publications in journals of national and international repute. He is also an avid mathematics enthusiast. He has already guided 10 PhD students and currently is supervising 5 number of PhD students. He has visited several countries like USA, France, Australia, Switzerland, Austria, Thailand, and China to attend international conferences or deliver invited talks. In NIT Rourkela, he held several positions like member of BOG, Dean SRA CCE, HOD Mathematics, Chairman, Central Timetable Committee, Warren, etc. He is a life member of the Fibonacci Association, the Computer Society of India, and the Odisha Mathematical Society. In addition, he has worked and is working as a member of Board of Studies of several universities and institutes. So once again, I welcome you, Dr. Panda. So now I request you to deliver your today's talk.
Thank you. First of all, I would like to thank SOA University, and in particular ITER and my nanny to invite me for delivering this talk. I can't say ma'am because she was my nanny and she'll be my nanny forever in whatever position she will be. So I also thank the HOD and other members for organizing this such type of events weekly. It will definitely enhance the research ability of students of your institute. So I'll present now. Let me, share. So is it visible?
Not yet.
It might take time. Not yet?
No, sir.
No, not yet.
Now
it's coming.
Sorry. It is stopped now, I think. Just give the comment stops. Visible, still visible.
Again, I think it went away. Not visible.
Let me. Because it is not visible, is it not visible? I should, give the comment stop sharing.
Okay. You can start again. I think it will be all right.
So it is taking time, I think. So let me wait for some time.
Okay. Yes. Now,
Okay.
yes, yes, it came
Okay.
now.
So the title of my talk is so simple that I believe that everybody will understand how to generate the natural numbers. So actually, natural numbers are God's creation, and it is really generalizing natural number is really a very difficult task. Really, we are not generalizing; we are identifying substances of natural numbers which will behave like natural numbers. So I'll start with a famous quote by Gauss. Mathematics is the queen of all sciences, and number theory is the queen of mathematics. So activity lies in mathematics and in particular in number theory. So the talk outline of the talk is as follows: natural numbers, sequences, generalized natural numbers, generalized triangular numbers, generalized conic numbers, and so there are some conjectures at the end. So as we know, what are the natural numbers? These are the counting numbers first known to mankind, 1, 2, 3, 4, etc. And we know that there is no end to it, because if n is any natural number, n plus 1 is the next big number. There are many fascinating facts for natural number, you know them, and the sequence is still mysterious, and many more fascinations are yet to be discovered. So the most simple thing, the first natural number is 1, the second is 2, third is 3, nothing great in that. And in this sequence, the first number is 1, second is 2. So can we start a sequence where the first number is 1 and second number is 3 or 4 or 5 or 6 or something? And we want that the new sequence should satisfy some important properties of natural numbers.
Sorry, hello. Sorry to interrupt
Yeah.
you, sir, but your slides are not moving actually. Means only we can see the title page only, the starting one.
Yes, there is the problem. Sai Gopal is there, I think.
Yes, sir.
I have sent him my slides. He can start.
Okay, sir. Let me share.
Yeah. There is a problem, I am telling. Let me mobile is not good. This is happening. The network is slow.
Yes,
Yes,
sir.
slow.
Now your slide came actually. Your natural number.
Okay.
Now the slide came.
Yeah. So is it the second side? Yeah, is visible. Natural numbers is the natural numbers. So in the natural numbers, first number is 1. Is it visible now?
Yes, it is visible.
The second is 2, third is 3. This is visible. What I was telling. So natural numbers of the form 2n are known as even numbers, and those of the form 2n minus 1 are known as odd numbers. Very simple fact. That the natural numbers of the form n into n plus 1 are known as conic or rectangular numbers, and when divided by 2, that is n into n by 2, are known as triangular numbers. Natural number x is a conic number if 4x plus 1 is square, because 4n into n plus 1 is 2n plus 1 whole square, and it is a triangular number if 8x plus 1 is square. So if we multiply by 8 and add 1, it will be again 2n plus 1 square. And another fact about triangular number is that if x is a triangular number, then 9x plus 1 is also a triangular number. For example, 1 is a triangular number, so 9x plus 1 is 10. 10 is the fourth triangular number. 3 is a triangular number, and 9 into 3 plus 1, 28. 28 is also a triangular number. It is the seventh triangular number, and so on. And the important thing is that x is a triangular number if and only if 8x plus 1 is square. X is a conic or rectangular number, that means a number of the form which is product of two consecutive natural numbers if 4x plus 1 is square. Is visible? Next slide. Hello?
Yes. Yes.
Yeah.
Visible,
There is
sir.
a problem. Yeah. So
Visible.
let A1, A2, An be a sequence of integers, any sequence of integers. It is called a recurrent sequence if for each n, An is function of the previous n minus 1 numbers. It not be all the numbers, previous n minus r numbers. And the relation An is equal to f of An minus 1, An minus 2 to An minus r is known as a reconciliation of order r, because the nth number depends on numbers up to order n minus r. If for each n, An is equal to f An minus 1, f n minus 2, if it is a function of just two previous numbers, then it is called a binary reconciliation, and the sequence An is known as a binary recurrent sequence. If An equal to Can plus Dn minus 2, then it is called a linear homogeneous reconciliation. If we add a constant here, something, suppose n or constant or something here, then it will be called a non-homogeneous reconciliation. But binary, this is now binary as linear and homogeneous. The Fibonacci sequence is a binary recurrent sequence, and we know it is defined like this: F0 is 0, F1 is 1. Or
Sir.
some people say, yeah.
Hello, sir.
Yeah. Please
So,
tell me.
again, your slides are not moving. We can see the slide natural numbers.
So let me do something.
Sir, make it full screen, then use slide mode. That will
You can
do
see
it.
the slide.
It is full screen. I should first make full screen and
No,
then
yeah. Let us do that.
then present.
Let us do that.
Stop presenting first.
No, here also you can do, sir.
It is full screen.
No, now it is blank.
Sir, your voice is also breaking.
As I was telling, the same problem is occurring.
This is the only. Everywhere this is the.
This is actually our institute. Fiber is yet to come to my house. We are also inviting the Geo people to give connection, but it will take some time. So this is the problem. And if an institute of ours will face problem like this, then what can you say about other places?
Okay, Dr. Gopal, you can share the slide if possible. Now,
The slide is it
okay,
not
Dr.
visible?
Gopal, please.
Yeah, is it
Let us-
visible? Let 1, 2, 3. Or should I have already sent slides to Sai. He can present. Sir, he can.
Now, Gopal Sai is presenting. Yeah.
Visible. A1, A2, A3.
He's trying. He's going for.
Yeah.
Yeah. Now it's running now.
Yeah. So,
Sir, you please instruct Sai Gopal sir to move the slides.
yeah. Sai, are you here?
Thank you.
Yes, sir. Yes, sir. I am sharing the slide,
Right,
and
let me
you can let me know when to move.
but the slide now I am presenting. I have to stop sharing, I think.
Yes, sir.
Yeah. I have to stop sharing. Then you have to.
हाँ सर अपन स्टॉप कर दियंतु साई की इंस्ट्रक्शन देले साई मूव करेबे स्लाइड
ठीक अछि अच्छा Sai already have started. Yeah. Sai, just make it full screen.
Yes, sir.
Yeah, just make full screen. Is it full screen? Say no problem still for me because I have a big screen. Full screen. The glass below the screen. This glass below the screen. No. Below. Take it. There's a glass like thing. No, next one. Yes, this one. No, next. Yes, this. Click this.
Is it fine, sir?
I'm seeing it's not full screen, but it is okay for no problem because my screen is big. So this is about the Fibonacci sequence. The Fibonacci sequence is a binary recurrent sequence and defined by Fn is equal to Fn minus 1 plus Fn minus 2. And the first two terms are taken as F0 is 0, F1 is 1, or F1 is 1 and F2 is also 1. Is it visible to everybody?
Yes, sir. Yes.
Yes, sir.
Yeah.
Yes, sir.
Next slide. I think I have to open my slide also.
Dr. Sai Gopal,
Yes, sir.
please move the next slide. Go to the next slide.
Sir, I have already done, sir.
But it is not coming here. Whatever you speak, sir, offline is offline, online is online.
Yeah.
Lot of many problems we are facing.
Connectivity is a problem, and actually,
No,
Geo at present we have difficulty. I am receiving net from telephone connection from our institute, so that's why it's very slow. So is it possible to move, or you have moved and not working?
Yes, sir, I have done, but whether you people can see or not, I don't know. Next slide पे है sir.
Let me mobile. Change the connection. Not working. Recurrence. It is showing recurrence sequence.
Yes, sir. Recurrence
Not the
sequence.
next one. Go to the next slide.
This one, sir.
I'm saying the same thing. Let A1, A2, A3 be a sequence of integers. If it will work from your side, if everybody can see, then I can see my own slide and also discuss. Yeah. So the Fibonacci sequence. Yeah, this is the next slide, I think.
Yes, sir.
Yeah. So the reconciliations are also known as differential equations, and several techniques and standard techniques are available to solve differential equation, and they are similar to methods used for solving the differential equations. Here is the important point comes. The natural numbers are solution of the first order linear recurrence. Xn is equal to xn minus 1 plus 1. We know each natural number, succeeding natural number is previous 1 plus 1. And you can start with x0 is 0, this is the initial condition, or x1 is 1 also. But the most important second order reconciliation which the natural number satisfy and which will be useful for us is xn is equal to 2xn minus 1 minus xn minus 2 with two initial conditions, x0 is 0 and x1 is 1. So you can see this is not like the first one. This is a first order reconciliation, this is second order reconciliation. And if you put x0 is 0 and x1 is 1, you can see that x2 is 2. If you put x1 is 1 and x2 is 2, for example, 2 into 2 minus 1, then you will get x3 is 3, and so on. So this reconciliation represents all the natural numbers. And if you move to left side, it will represent all the integers. So the multiplied 2 here, xn equal to 2xn minus 1, on the right hand side has an important role to play. We can replace these 2 by any arbitrary natural numbers. Then what will happen? Xn will become a subsequence of natural numbers. It will not adjust all the natural numbers, but if we replace it by any other natural number, it will be a subsequence of the natural numbers. Next slide. Yeah. So the sequence xn defined by xn plus 1 is a times xn minus 1. Here I have replaced the 2 by a, an arbitrary natural number with same initial condition x0 is 1, x1 is 1. is a natural generalization of the sequence of natural numbers, because for natural numbers we have a 2 in place of a, this a, first a, and if we take an arbitrary a, then it will serve as a generalization of the natural numbers, and this particular sequence so generated for any arbitrary greater than 2, the sequence is known as a balancing like sequence, and it is denoted by BL A minus 1. A is the coefficient here, and minus 1 is the coefficient in the second term. Actually, the balancing like numbers, they didn't come to existence in this way. They are obtained as a generalization of the balancing numbers, sequence of balancing numbers, and the balancing numbers are defined as Bn plus 1 is equal to 6Bn minus Bn minus 1 with same initial conditions. And this was first studied in a paper by myself and S.S. Raut, who is a faculty of Institute of Mathematics, a class of recurrent sequence exhibiting some exciting properties of natural numbers. Next slide. Yeah. But the actual definition of balancing numbers is this. It is actually if a B is called a balancing number if such a Diophantine equation holds. That means if the numbers from 1 to B minus 1, the sum is equal to the sum from B minus 1 to sum B plus R for some R, then we call B the balancer corresponding to, sorry, we called R the balancer corresponding to B. So just take natural numbers from 1 to some length. If you delete a number in between and if the sum of both sides are same, then the deleted number is not a balancing number. For example, if you consider the natural numbers from 1 to 8 and delete 6, then the sum from 1 to 5 is 15. And we have deleted 6, so 7 and 8 remains, so 7 plus 8 is also 15. Similarly, if we consider natural numbers from 1 to 49 and delete 35, then the sum from 1 to 34, one can calculate easily, is same as the sum from 36 to 49. And same thing happens for other numbers. For 204, the sum from 1 to 203 is the sum from 205 to 288. So these are the examples of some balancing numbers, and they can obtain a solution of reconciliation discussed in the previous slide. The balancing numbers are important in some aspect. The square of a balancing number is a triangular number. So it is a triangular number as well as a square is known as a square triangular number. And all the square triangular numbers are obtained as square of balancing numbers. There is no other way to obtain square triangular numbers. They adjust all the square triangular numbers, the square of balancing numbers. Similarly, the product of two consecutive, this is not triangular, it is actually a balancing. This triangular, consecutive, after consecutive, there is a word triangular, but it is actually balancing. Balancing number is also a triangular number as well as a pronic number. Means the product of two consecutive balancing numbers can be written as something k into k plus 1 by 2 or x into x plus 1. It can be written in two ways. And these products, consecutive products, are the only numbers which can be, which is a triangular number as well as a pronic number. No other numbers are of this form. Next slide. And this is published in a paper in 1999 on the square root of triangular numbers. Okay. So these are examples of some generalized, balancing like sequences. We have, when a is 2, we got the natural numbers. Xn plus 1 is axn minus xn minus 1 with x0 is 0 and x1 is 1. So first term is this, second term, third term, fourth term, this is the natural numbers when a is 2. When a is 3, we'll get 1, 3. The second number has an important role to play. Then 3 into 3 minus 1, 8. 8 into 3 minus 3, previous one, 21. 21 into 3 minus 8, 55. 55 into 3 minus 21, 144. When a becomes 4, the first two numbers are 1, 4. And 4 into 4 minus 1 is 15. 4 into 15 minus 4 is 56 and so on. So for other numbers also, we can proceed like this. And in general, for an A arbitrary A, the numbers are like this. X1 is 1, X2 is A, X3 is A square minus 1. You put any value of A, you will get these numbers. X4 is equal to A cube minus 2A, X5 is equal to A to the power 4 minus 3A square plus 1, and X6 is equal to A to the power 5 minus 4A cube plus 3A, and so on. This is the general form of balancing like numbers for any arbitrary A. If you put A is 2 here, you will get the natural numbers. For example, if you put A is 2, you will get 2 here. Here, 2 square minus 1 is 3. Then 2 cube minus 2A. Now 2 cube is 8 minus 2 into A is 4. You will get 4 and so on. You will get all natural numbers when you put A equal to here. Next slide. Yeah. So the balancing sequence as well as the balancing like sequences behave like natural numbers. So the sum of first 2n minus 1, first n odd balancing like numbers, x1 plus x3 plus x5 up to x2n minus 1. This is the first n odd index balancing like numbers. This is equal to sum of nth balancing like number. And this generalizes 1 plus 3 plus up to 2n minus 1 is equal to n square. This is a well-known property of natural numbers. The sum of first n odd natural numbers is equal to n square. Similarly, x2 plus x4 up to x2n. This is sum of first n even indexed balancing like number. This is equal to xn into xn plus 1. Nth balancing like number plus n plus first balancing like number. And this generalizes 2 plus 4 plus 6 up to 2n is n into n plus 1. This is property of natural numbers. Next one is xn plus r into x of n minus r is xn square minus xr square. This generalizes n plus r into n minus r is n square minus r square. This is not equality. This is an error. So this is n square minus r square. This is an error. Next slide, sir.
Done, sir.
Yeah, visible. No problem. But you have not maximized it. Not full screen. You are not using full screen mode.
Sir, actually, when I use full screen mode, the same problem happening as in case of
Okay, it's fine. So for each natural number n, 8 times square of nth balancing number. The balancing number is a solution of that equation with a is equal to 6. 8 bn square plus 1 is a perfect square, and its positive square root cn is known as the nth Lucas balancing number. This is a definition. The reconciliation for Lucas balancing number is same as that of balancing numbers. Cn plus 1 is 6, cn minus 1. Of course, the initial terms are different. C0 is 1 and C1 is 3. Unlike B0 is 0 and B1 is 1. And together with the Lucas balancing number, the balancing number and Lucas balancing number, they satisfy many interesting properties. Cn plus root 8 bn whole to the power k is equal to cnk plus root 8 bnk. So this resembles the Bhubaneswar property. Cos x plus I sin x to the power n is cos nx plus I sin nx. So what is the only difference? We have root 8 here and we have I here. Otherwise, the properties are similar. Next one. So this is something more general. Cm plus root 8 bm into cn plus root 8 bn is cm plus n plus root 8 bm plus n. This is the m plus nth Lucas balancing number. And it is precisely equal to 8 into bm plus n square plus 1. Further, cm plus n is equal to cm cn plus 8 bm bn, and bm plus n is bm cn plus cm bn. This resembles the identity sin x plus y is sin x cos y plus cos x sin y. This bm plus n, this one. Similarly, c2n is equal to cn square plus 8 bn square, and b2n is 2 bn cn, and this resembles the property sin 2x is 2 sin x cos x. So these things are published in a paper by myself as known as some facilitating properties of balancing numbers in the proceedings of an international conference. So next slide, Sai. So for each a greater than 2 and for each n, dxn square plus 1, xn is the nth balancing like number, and d is a square minus 4 by 4 is a square, and its positive square root yn is known as a Lucas balancing number, Lucas balancing like number. The reconciliation for Lucas balancing numbers is same as that of the corresponding balancing numbers, like yn plus 1 is ayn minus yn minus 1. However, the initial constants are defined just like for Lucas balancing numbers. Y0 is 1 and y1 is a by 2. In case of balancing numbers, y1 was 3. 3 is 6 by 2. A is 6 in case of the balancing numbers. And the balancing like sequence corresponding to a equal to 4. I have already shown it. It is 1, 4, 15, 209, something like that. And d is equal to 3. Why? A square minus 4 by 4. So 4 square minus 4 by 4 is equal to 3. D is 3. And one can note that dx1 square plus 1 is 4 because x1 is 1. dx2 square plus 1 is 49 because x2 is 4. 3 into 4 square, 16, 4 in, so 3 into 16 plus 1 is 49. Similarly, dx3 square plus 1, 3 into x3 is 15. 15 square plus 1 is 676. This is 26 square. And therefore, the corresponding Lucas balancing like numbers corresponding to a is equal to 4 are y1 is 2 square root positive square root of first one, y2 is 7 square root of 49, and y3 is 26 square root of 676. So all the properties of balancing and Lucas balancing numbers we have discussed are true for the sequence of balancing numbers because the balancing sequence of BLA minus 1 and the corresponding Lucas balancing like sequence means whatever property of balancing numbers we have discussed in the previous slide, they holds good with d replaced by 8. D replaced by 8. So in place of root 8, we will be having root d. In the previous slide, whatever we have discussed, they holds for all the balancing like sequences. Next slide. So it is the same slide. I'm not seeing the next slide.
I have changed, sir.
You have changed, but it might take time. Again, network problem. I think I should switch off my video. That is taking a lot of bandwidth. No, it's the same slide. For a greater than 2 and for each n, I'm seeing here. Slide number 15. You should go to slide number 16.
Okay.
Yeah. So a triangular number we have discussed earlier is a figure 8 number, which is the number of dots required to form a discrete triangle. So 1 dot is the initialization. With 3 dots, we can form a triangle. Next, we can form using 6 dots, means put 3 dots, again above 2 dots, again 1 dot. So if you put 4 dots first, then in between you can put 3 dots, then 2 dots and 1 dot. So this there, but T1 is 1, T2 is 3, T3 is 6, T4 is 10, T5 is 15, T6 21, and so on. And in general, the nth triangular number is, if you start putting n dots in the bottom, then n minus 1 and so on. So 1 plus 2 up to n is n into n plus 1 by 2. Next slide. So there are some properties of triangular numbers. I have already told 8 times a triangular number plus 1 is square. 8 tn plus 1 is precisely 2n plus 1 whole square. Tn minus 1 plus tn, n minus first triangular number plus nth triangular number, this is equal to n square, and 9tn plus 1 is a triangular number for each n. So what we want, is there a way to generalize the triangular numbers using balancing like sequence? Because we claim that the balancing like sequences are generalizations of the natural number sequence. So can we generalize the triangular numbers to balancing like sequences? And the answer is affirmative. But the third property, the first two property we can fulfill, but the third property cannot be fulfilled in this generalization. The third property has to be sacrificed. So next one. So for any positive integer a, the nth triangular like number corresponding to the sequence balancing like sequence with a minus 1, BL a minus 1 means defined by xn plus 1 is equal to a xn minus xn minus 1. It is this is a definition. It is defined as tau n of a because it will depend on n as well as its value will depend on what a we are using. So xn, this is equal to xn into xn plus 1 by x2. For triangular numbers, we define it as n into n plus 1 by 2. So we prefer to define xn into xn plus 1 by x2. And x2 is equal to a for BL a minus 1. This sequence is like this 1 a square minus 1 and so on. So x2 is equal to a. So it becomes xn into xn plus 1 by a. And this generalizes the definition of triangular numbers. Since when we put a is equal to 2, if a is 2, then xn becomes n. And xn becomes n means this becomes n into n plus 1 by 2. The identity, well, look at this identity, tau n minus 1 a plus tau n a. So tau n minus 1 is xn into xn minus 1 by a. Tau n minus 1 is xn into xn minus 1 by a. And tau n a is xn into xn plus 1 by a. So if we sum it, what we'll get? Xn, if we take xn common, we'll be getting xn plus 1 plus xn minus 1. And because of the reconciliation, xn plus 1 is axn minus xn minus 1. So xn plus 1 plus xn minus 1 becomes axn. And therefore, xn into axn by a is equal to xn square. Though that means the sum of n minus 1th triangular number and nth triangular like number and nth triangular like number is equal to square of nth balancing like number. And this is similar to tn minus 1 plus tn is equal to n square. Next slide. Yeah. The triangular like number tau n satisfies this property. This can be verified. A square plus 2a into tau n a plus 1 is equal to xn plus 1 plus xn whole square. For example, if you take a is equal to 4 and n is equal to, suppose we take 2, then this becomes 4 square plus 2a, 4 square plus 2a, this becomes 24, 4 square plus 2a. So if a is 4, this is 4 square plus 2a, 24, 2a is 8, and tau n a. So if we take n equal to 2, then tau 2 is 4. So 20 into 4 plus 1. 20 into 4 plus 1 is 121. 121 is 11 square. And this is your 4 plus 7. Xn plus 1 plus xn, yeah, square, 11 square. And this serves as a generalization. 8tn plus 1 is 2n plus 1 whole square. So if you replace, suppose you think that this is the natural numbers a is 2, then what will happen? N xn plus 1 will be n plus 1 and xn will be equal to n. So n plus 1 plus n is 2n plus 1. And in addition, one extra property also it satisfies. A square minus 2a plus tau n a plus 1 is also equal to xn plus 1 minus xn whole square. So here if a is 4, then 4 square is 16 minus 2a is 8. 8 tau n a is how much? 1 into 4 by 4. 4. So this becomes 8 into how much? If a is 4, tau 2a. Tau 2 will be how much? Tau 2 will be, tau 2 is 4. 4 into next term. Next term is 15. 4 into 15. 4 into 15 is 60. 8 into 60 plus 1. Tau 2 is 15. So 8 into 60 plus 1. How much? One can verify. Taking numerical value, one can verify. This is not a big deal because if you put age 4, the values are known. This will be, if we to take n equal to, then x2 into x3 by a is 3. Next slide. With numerical values, it can be verified. So I have considered this example. So consider the sequence BL4 minus 1. Here, xn plus 1 is 4xn minus xn minus 1, and this is the initial condition. The terms of the sequence are 1, 4, 15, 56, 209, and 780, and so on. A square plus 2a is 24. A square minus 2 is 8. That's what I have telling. And the triangular-like numbers are tau 1, 4 is 1, tau 2, 4 is 15, tau 3, 4 is 210, and so on. And one can see tau 1a plus tau 1 of 4 plus tau 2 of 4. 15 plus 1 is 16, that is 4 square. X2 square. Tau 2 4 plus tau 3 4, that is 225, which is x3 square. X3 is 15. And a square plus 2a into tau 1a plus 1, this becomes 25, which is equal to 5 square. A square minus 2a into tau 1a, this is 9, which is equal to 3 square. Further, a square plus 2a into tau 2a plus 1 is 169. If we substitute a is 4 here. And a square minus 2a into tau 2a plus 1 is 121, which is 11 square. Similarly, if you go to tau 3a, you will get 5041, that is 71 square and 41 square. Next slide. These are some verifications. So, but one should take precaution. If only one of a square plus 2a into tau plus 1 and a square minus 2a into tau plus 1 is a perfect square, then tau need not be a triangular-like numbers. Actually, these conditions are necessary. Tau can be a triangular-like number only if both are perfect squares, not just one. For example, in the sequence BL3 minus 1, 3 minus 1 means xn plus 1 is 3xn minus xn minus 1, x0 is 0 and x1 is 1. The terms are 1, 3, 8, 21, 58, 144. And the sequence of triangular numbers are, this can be calculated, 1, 8, 56, 26, 40, and so on. If a is 3, a square plus 2a is 15, a square minus 2a is 3. 15 tau plus 1 is a perfect square. For tau is 13. If tau is 13, then 15 tau plus 1 is a perfect square. And if tau is 13 and tau is 17 both, 15 tau plus 1 is a perfect square. But neither 13 nor 17 is a triangular-like number, because for this, both properties should be satisfied. A square minus 2a into tau plus 1 should be also a perfect square. Similarly, 3 tau plus 1 is a perfect square for tau equal to 5 and tau equal to 16. But neither 5 nor 16 is a triangular-like number in BL3 minus 1. So both the conditions need to be fulfilled. Thus, tau is a triangular-like number corresponding to this balancing-like sequence if both a square plus 2a into tau plus 1 and a square minus 2 into tau plus 1 be perfect squares. And when a is 2, we are with our natural number sequence when a is 2. And in that case, a square plus 2a into tau plus 1 is 8 tau plus 1, and a square minus 2a into tau plus 1 is equal to 1. So this is always a square. Therefore, we verify just one condition. 8 tau plus 1 is should be a perfect square in case of natural numbers and in case of our ordinary triangular numbers. So the next question one may come to one's mind is there a balancing like sequence for a greater than 2? Is there a balancing like sequence with the property that all its triangular like numbers, means numbers of the form xn into xn plus 1 divided by x2, or which is equal to a, are also triangular numbers? That I'm giving hints on this point. So is there a balancing like sequence such that all its triangular like numbers are also triangular numbers? So I will answer it in affirmative. Next slide. The terms of the sequence BLA minus 1, for generally we have already discussed, are 1, a square minus 1, a cube minus 2a, we are getting it from the reconciliation. Xn plus 1 is Axn minus Xn minus 1. X0 is 0 and X1 is 1. So the first triangular like number tau1a is 1 into A by A. X2 is A here, 1. This is true for all balancing like sequences. The second triangular like number tau2a is A into A square minus 1 by A, means X2 into X3 by X2. X2 that is A square minus 1. And A square minus 1 is a triangular number if and only if 8 into A square minus 1 plus 1 will be a perfect square. But 8 into A square minus 1 plus 1 is 8A square minus 7. Is if this is square, B square for some B. And in this case, A must be a almost balancing number of second kind. Actually, I'm not going to discuss about almost balancing numbers. They have different definitions, but almost balancing numbers are related to balancing numbers in this way. They are either of the form n plus first balancing number minus twice of nth balancing number, or twice of n plus first balancing number minus nth balancing number. These are all the almost balancing numbers. The third triangular like number tau3a is x3 into x4 by a. So x3 is a square minus 1 and x4 is a cube minus 4a divided by a. That is equal to a square minus 1 into a square minus 2. This is the form of third triangular like number. And this is a triangular number if 8 times this number, a square minus 1 into a square minus 2 plus 1 is a perfect square. That is 8 tau3a plus 1, which is 8 e to the power 4 minus 24 square plus 17 is a perfect square. And since 8 e to the power 4 minus 24 square plus 17 is of the form 8 into a square minus 2 whole square, it can be written like this, plus 8 into a square minus 2 plus 1, then a square minus 2 must be a cobalancing number whenever tau3 is a triangular number. So what is a cobalancing number? A cobalancing number is just like a balancing number. It is a number such that the sum from 1 to b is equal to sum from b plus 1 to b plus r from sum r. And b, there is a property of cobalancing number. B is a cobalancing number if and only 8b square plus 8b plus 1 is a perfect square. And the cobalancing number satisfy a different reconciliation. Bn plus 1, small bn plus 1 is 6bn minus bn minus 1 plus 2. So the reconciliation is non-homogeneous. And the initial conditions are b0 equal to b1 equal to 0. And all the cobalancing numbers and cobalancers, all the cobalancing numbers are balancers. Balancers are related to balancing number sequence, and all the cobalancers means this r here, small r, are balancing numbers. Actually, the balancing sequence and the cobalancing sequence are very closely related to each other. And this appears in a paper I've written, cobalancing numbers and cobalancers jointly with P.K. Ray, Prashant Ray, you must know. Next slide. So for a greater than 2, both tau2a and tau3a are triangular numbers if and only a is 4. This is an important actually theorem, but I'm not written everything. Only for a equal to 4, both tau2a and tau3a are triangular numbers. These are triangular like numbers corresponding to some a. And when a is 4, both are triangular numbers. These are triangular like numbers corresponding to a equal to 4. All the triangular like numbers of this sequence BL4 minus 1 means defined by xn plus 1 is 4xn minus 1 are triangular numbers, because tau n4 can be written as x1 plus x2 up to xn into x1 plus x2 up to xn plus 1 divided by 2. This is there is a relationship. So all triangular like numbers of the sequence corresponding to a equal to 4, balancing sequence corresponding to a, balancing like sequence corresponding to a equal to 4 are triangular numbers. One can check tau1 4 is 1. Tau2 4 is 15. 15 is a T5 fifth triangular number. Tau3 4 is 210. 20th triangular number. Tau2 4 is 2926. 76 triangular number. Tau5 4 fifth triangular like number is 40755, which is 285th triangular number. And BL4 minus 1 means the balancing like sequence with a equal to 4 is the only sequence with the property that all its triangular like numbers are also triangular numbers, and no other balancing like sequence has this property. So this is there's a publication by myself and Sushri Sangeeta Pradhan. She recently, last year, got PhD. So the triangular numbers have a different property also. The nth triangular number, we write it as n into n plus 1 by 2, and also it coincides with the sum of first and natural numbers. But in case of balancing like sequence, the nth triangular like number is not equal to sum of first n terms of that sequence. Rather, something else is true. The nth balancing number of a given balancing like sequence is equal to sum of first n minus 1 terms of another balancing like sequence. For example, the nth triangular like number corresponding to the sequence BL A minus 1 means the reconciliation xn plus 1 is axn minus xn minus 1 is equal to sum of first n terms of the sequence BL A square minus 2 minus 1 means this is equal to the sum of the n terms of the sequence defined by xn plus 1 is a square minus 2 into xn minus xn minus 1. But in case of natural numbers, what will happen? A is 2 and a square. If a is 2, then a square minus 2 is also 2, and BLA minus 1 and BL a square minus 2 minus 1 they coincide because here a is 2 and a square minus 2 is also 2. So the terms of the sequence BL3 minus 1 means xn plus, defined by xn plus 1 is 3xn minus xn minus 1 are of this form 1, 3, 8, 21. How 21? 8 into 3 minus 3. 55 and so on. The triangular like numbers are tau 1 3 is 1 because 1 into 3 by 3, tau 2 3 is 8 because 3 into 8 by 8, tau 3 of 3 is 56 because it is equal to 8 into 21 by 3 and so on. And observe that tau 1 3 equal to 1, that is equal to x1, but tau 2 3 is 8 while x1 plus x2, this is the second triangular like number, but x1 plus x2, x1 plus x2 is how much? Equal to just 3. So 8 is not equal to 3. Tau 2 3 is 56 and it is not equal to x1 plus x2 plus x3 because x1 plus x2 plus x3 is 1 plus 3 plus 8, which is much less than 56 and so on. But in general, tau n3 is not equal to x1 plus x2 plus xn of the same sequence. If a is 3, then a square minus 2 is 7. And if we look at the sequence BL 7 minus 1, the terms are x1 is 1, x2 is 7, x3 is 7 square minus 1 is 48, x4 is 48 into 7, 7 into 48 minus 7 is 329 and so on. And here, for example, tau 3 of 3 is 56. Tau 3 of 3 is 56 here. And if you take sum of 3 terms, 1 plus 7 plus 48 is 56. So the sum of first n terms of BL3 minus 1, sorry, the nth triangular like number of BL3 minus 1 are equal to sum of first n terms of the sequence BL7 minus 1. So this is something different for balancing like numbers and triangular like numbers. So the generalized pronic numbers will define the triangular numbers. Twice of a triangular number is a pronic number. That means numbers of the form n into n plus 1 are called pronic numbers. And a natural generalization of the nth pronic like number is tau n is xn into xn plus 1. Actually, time, please stick to time. If it can be terminated any time. Hello? Time. Because I have exceeded time because of interruptions. Yeah? We can terminate, no problem.
About 27.
Yeah? How much?
12 hours, 27 minutes, sir.
27 minutes. Okay.
So,
Okay.
yeah. So
No problem.
3 minutes left, I think. 5 minutes maximum. You can carry on.
Okay. So the first few pronic like numbers are given like this, and the sequence satisfy reconciliation pi n plus 1. Pi n a is the nth pronic like number. pi n plus 1 is a square minus 2 pi n a plus pi n minus 1 into a plus 2. And this is comparable to the reconciliation of Punic numbers as Pn plus 1 nth Punic number. And in Pn plus 1 is n into n plus 1. It's 2Pn minus Pn minus 1, with P0 is 0 and P1 is 2. Next slide. You can skip time. Yeah. So there are some conjectures while finding the values of x, so that tau 3x is triangular. We come across this equation: 8x to the power 4 minus 24x square plus 17 is equal to y square, and the fulfillment of which makes tau 3x a triangular number. And this equation has three known solutions: xy equal to 1, 1, 2, 7, and 4, 41 in positive integers. And it is believed that no further positive integer solution exists. Of course, positive or negative doesn't matter. No, if a positive solution is there, then there is a negative solution also. Next slide. So these are some conjectures related to my talk. All solutions of the Diophantine equation 8x to the power 4 minus 24x square plus 17 equal to s square in positive integers are 1, 1, 2, 7, and 441. Means no other solution exists. This is the conjecture, but yet to be proved. The conjecture 2 is no covariance number Bn other than B2 equal to 2 and B3 equal to 14 has the property that Bn plus 2 is a perfect square. And the third one is no covariance number B other than B0 equal to B1 equal to 0 and B2 equal to 2 and B3 equal to 14 has the property that B plus 1 is a triangular number. Next slide. So these are some observations. For students may think about this. A balancing like sequence is defined like this: axn minus xn minus 1 is the x plus first term. And if we define backward, we can see that x minus n is minus of xn. So out of the infinite number possibility for balancing like sequence, BL2 minus 1, this is the natural numbers. Actually, if we define x minus 1, x minus n equal to xn, then it constitutes the sequence of natural numbers. But when we generalize and go to balancing like sequence, even we go to backside also with the relation x minus 1 is minus n is minus xn, the ring property is lost. So one can think what algebraic structure can be defined on the sequence of both positive and negative balancing like numbers. Another interesting thing is that the balancing like sequence BL3 minus 1, when A is 3, it coincides with the even in-text Fibonacci sequence. So it is also related to Fibonacci sequence, while the nth term of the sequence BL7 minus 1 is also related to Fibonacci sequence as F4n by 3. BL3 minus 1, the even index Fibonacci sequence, has a special property. Any three consecutive terms of the sequence is a Diophantine triple. That means the product of any two of the three terms raised by 1 is a perfect square. This one, BL3 minus 1, the terms are even index Fibonacci number 1, 3, 8, 21, 55, 144. And if we take the set 3, 8, 21, one can see if you take the product of any two and raise 1, it is a square. This is very fact. Same thing applies to 8, 21, 55, 21, 55, 44. So this is a very important property. Next one, next slide. Okay, so I'll conclude my talk with a beautiful quote by the famous Hungarian mathematician Paul Erdős. So wherever numbers beautiful, it's like asking why is Beethoven's 9th symphony beautiful? I'm not saying, Erdős is saying. If you don't see why, someone can't tell you. I know numbers are beautiful. If they aren't beautiful, nothing is. So this is the end of my talk. Thank you. Any question, please?
Yeah, please ask questions.
Any questions?
I'm sorry for the interruption, but we have no control over the network.
It's okay. It's okay.
All right.
No problem.
You may come over this problem.
It's okay. It's okay. ठीक है Gopal. No problem. So any questions?
Anyway, if there is no question now, then you can ask me or write me or whatever you want. You can do.
Yeah.
or Sai is there, he can answer my question.
Yeah. No problem actually, because our teachers are engaged in classes.
Hello,
so
sir.
Yeah.
Hello, sir. I have a query.
Yes.
Yeah.
Sir, how Lucas number is different from Fibonacci number?
See, they are defined by means of the same reconciliation. Only the initial terms are different. For example, Fibonacci sequence is defined as Fn is Fn plus 1 minus Fn minus 2. The start 2 and F1 is 1. The Lucas numbers are defined by the same reconciliation. Ln plus 1 is Ln minus Ln minus 1. But L1 is 1 and L2 is 3. Or you can say L0 is 2 and L1 is 1. This is the only difference. Otherwise, there is no difference. Same reconciliation.
So phi in Lucas series, the initial value is 2.
If you do the backward calculation, you will get. If you try with 1, 3, then next term is sum of two previous terms. If you proceed like this, that will also give you a method to get the terms in a backward manner. If you calculate backward, you will get 2.
Okay, sir. Thank you, sir.
Because if L0 is 2 and L1 is 1, then only L2 will be 3. Backward calculation.
Okay,
so
sir.
actually, any further question you can ask Sai Gopal. He's very competent on these topics. And I want to announce that there's a good news for Sai. He knows also. It is actually he submitted his thesis in March, but it was so much delayed by we did not get the report of one foreign examiner, and the thesis was resent to another examiner. And recently we have got the report of Sai, and the report is really very excellent. And one examiner has praised that it is more than the average standard of thesis of North American University. And his Viva is scheduled on 9th at 11 a.m. So I request the HOD to make him free during that time and make proper arrangement of so that he can.
Sure. There will be no problem. So congratulations, Sai, and congratulations also goes to you, Dr. Panda, because you are his guide.
No. Sai is very hardworking.
Thank you.
And he'll be the asset for your student.
Okay.
Very hardworking.
So thank you, Dr. Gopal Panda, and I am sure that our faculty members must have benefited from this beautiful talk. And thank you again for the nice presentation. Now I request and for this webinar again we met after such a long time.
No problem.
So let me inform you all. Let me inform you all that Dr. Panda, while starting his talk, he told me that Nani. So if you were not knowing the word Nani means elder sister, because I was senior to him during his PG and my MPhil courses at Samalpur University. So he calls me Nani, that's why. So thank you, Gopal. Okay. And now I request Dr. Avijit to offer the vote of thanks from our department. Dr. Avijit. Abhijit has been disconnected. Okay.
Okay, Nani, this is a formality.
Okay. So actually, I thank our founder president of this university, Dr. Manoj Ranjan Naik, because he is the brain behind this Saturday webinar. And we are thankful to all the participants. You have, in spite of your classes and adjusting your classes also, adjusting your times, you could participate in this webinar. Okay, Abhijit is there. Abhijit, you have joined?
Yes.
Yeah.
I lost connection.
Yeah. Continue your vote of thanks.
So, at the end of the 16th Siksha Anusandhan weekly academic lecture, I, Dr. Abhijit Sutradhar, co-convener of this weekly series of webinars organized by the Center for Applied Mathematics and Computing, shall take liberty of proposing vote of thanks.
Again, Abhijit, you have been disconnected. Okay,
Yeah.
thank you, everyone. Thank you,
And students,
Gopal. from my side, and
Thank you, Nani.
thank you. Okay.
And one more
Okay.
thing I want to announce, you can join the defense seminar. Anybody can join the defense seminar of Sai Gopal. I will send the link in Google Meet.
Yeah, sure,
So
sure.
everybody is welcome.
Okay.
Because he is also from your institute now. Even if he is not there, you can join. Anybody wants, he can join or she can join.
We wish Sai Gopal in advance all the best for the defense viva. And
Thank you, ma'am.
okay, and in advance, congratulations also to you and your guide. Gopal, congratulations. Okay.
Thank you, Nani.
Thank you, everyone. So let us stop the webinar over here. Thank you.